Hello everyone, my name is Paolo Costa and I'm a researcher in Microsoft Research in Cambridge. In this talk I'll give you a short overview on Project Sirius, in which we try to answer the question, can we build a nanosecond optical network at data center scale? I'm sure you're all familiar with the Moore's law for CPUs, but a similar trend also applies to electrical switches. Every 2 years we have a new switch chip that has twice the boundary for the previous generation at roughly the same power and cost. And this is great because it allows to grow the network capacity without significantly affecting the power and cost. However, there is now a growing concern in the industry for how long this nice trend can continue. And this is probably the worst time for this to happen because we are also observing a spike in traffic demand driven by the availability of new devices such as AI accelerator or GPUs that can process data in excess of 1 terabit per second. So we think that this is a great opportunity to take a step back and see if there are new technologies that are non-CMOS dependent that can provide a new growth curve as we move in a post-Moore's era. And we think that optical switching could be a very promising candidate. So how can we switch packets using light? There are different ways in which this can be achieved. The specific technology we use in our project is called wavelength switching. It's based on two key components. The first one is called AWGR. It's a completely passive component. There are no transistors or buffers. It's basically etching of glass. And it has this nice property like a prism that it can redirect the light based on its wavelength or color. For example, if we have wavelength red, it will redirect on port 1, and if we have wavelength green, it will redirect on port 2. So we can combine this with a fast tunable laser, which as the name suggests is a laser that can tune very fast from one wavelength to another. And so by simply changing the wavelength of the laser, we can change the destination of the packet without requiring any packet processing in the network. Our goal is to use this technology to build a flat optical network that can scale to tens of thousands of nodes. So we want to replace the hierarchy of switches that we have in the core of our networks today with our passive core and using tunable lasers at the edge. What are the benefits? Well, first of all, since we are removing all electrical switches and transceivers in the core of the network, we can achieve a much cheaper network with a low power consumption. Second, since we don't have any buffers or packet processing in the network, we can achieve ultra low and predictable latency, effectively the speed of light. And finally, since we are reducing our dependency on CMOS, and since the core is passive and so it's bandwidth agnostic, we believe that this could be a future-proof solution as we move into a post-Moore's era. So how fast can we tune these lasers? Well, when we started the project in 2016, we were using off-the-shelf tunable lasers that were able to tune in about 1 millisecond. The challenge with this is that if we want to keep the overhead to about 1 millisecond, it means that the transmission slot needs to be 9 milliseconds, which as 100 gigabit per second is about 110 megabytes per slot. Now this might be okay if we want to reconfigure in between jobs, for example, but clearly it's not a great fit for data center traffic that can be very bursty. So we spent the next year in the project to really try to optimize this technology. And in the end, we were able to show a worst-case tuning time of less than 100 nanoseconds. Now, on the one hand, this was a great result. It was 4 orders of magnitude better than when we started. And we were also able to reduce the transmission slot to 900 nanoseconds. The problem was that at 100 gigabit, this was still 11 kilobytes, which is much bigger than the size of a packet today. And so this was the time in which we realized that if we really want to achieve packet level reconfiguration and go below the 100 nanosecond threshold, we need to fundamentally change the way in which we design tunable lasers. So we came up with a new design for achieving fast tunability. We implemented this onto a photonic chip that we got fabricated in external foundry. And using this, we were able to demonstrate sub-nanosecond tuning time between any wavelength to any wavelength. And this is great because it shows that we can now achieve, in principle, 9 nanosecond slots, which effectively means achieving a slot size of 100 bytes, which is very close to what you have today with electrical packet switches. Now, as you can imagine, this has been a long journey. So we first designed the chip in-house, then we got it fabricated in external foundry, then we got the chip back and we did die-level testing in our facilities in Cambridge, and then we got the chip package so we could integrate it in our test. Now, you can think at this point we are pretty much done, but in fact we are just at the beginning of our journey. Because the challenge is that having a fast optical switch is just the first step towards building a nanosecond optical network. But a big part of the challenge is how to build a system that can operate in such a very fine-grained time scale. And so we spend the rest of the project in really trying to design a system that was optimized for the nanosecond regime, and also to build a 4x4 prototype that effectively was able to demonstrate the feasibility of our idea. And we were able to show FPGA to FPGA traffic with an end-to-end reconfiguration latency of less than 4 nanoseconds. So why is it so hard to build a nanosecond optical network? The reason is that already when we moved from slow optical switches, say millisecond timescale, to microsecond timescale, there were a number of challenges that as community we had to solve, for example, scheduling or control plane. But now all this problem becomes much harder when you go to a nanosecond timescale. And on top of this, you also have new challenges that were not really critical in the millisecond or microsecond, but that now becomes absolutely crucial. For example, every time you switch from one destination to another, the receiver has to recover the clock of the new transmitter. And this is something that typically takes hundreds of nanoseconds. And so if you want to achieve nanosecond reconfiguration time, we need to reduce this by 2 orders of magnitude. And then the next challenge we have is that we only have 100 wavelengths, but we want to connect tens of thousands or hundreds of thousands of servers. So how we can achieve that? And then scheduling was already challenging in the microsecond world. In a nanosecond regime, it becomes extremely hard to the point that it might not even be possible. In fact, even if we had a schedule, that would be completely pointless unless we also have a time synchronization mechanism that enables to achieve nanosecond accuracy. And finally, since the physical parts of the network are changing every tenth of nanoseconds, TCP will not have enough time to converge to the correct rate, and so we need a new congestion control mechanism that enables to cope with this fast-changing world. Now, you might be tempted to see each of these problems as completely disconnected from each other and also belonging to different communities. But in fact, what we show in the paper is that by co-designing the whole stack from the ground up, and also by taking advantage of the unique properties of the cloud environment, we were able to come up with a solution that was much more efficient and much simpler. Unfortunately, I don't have the time to discuss in detail how we solved each of these challenges. However, in the paper you can find more information on the design of our nanosecond tunable laser, as well as the mechanism that we used to achieve a CDR lock-in time of less than 600 picoseconds and the time synchronization with sub-nanosecond accuracy. We also discussed how we scale our basic building block to be able to connect hundreds of thousands of servers with just 100 wavelengths, and also our scheduleless design that uses a cyclic schedule as opposed to on-demand schedule to orchestrate transmission. And finally, also how our congestion control can ensure predictable latency for short flows and high throughput for long flows. And as I was mentioning before, this was made possible by the fact there were a lot of synergies between all these layers. For example, the cyclic nature of the scheduling made it possible to simplify the design of the fast tunable lasers as well as the CDR, but also together with the passive core in the network and the lack of retiming, we were able to simplify the design of time synchronization, which in turn also helped for the CDR and congestion control. And there were other examples of this that you can find in the paper. What really excites us about this technology, it has the potential to change the way in which we manage resources and we design applications in our data centers. So today, as an application, you are restricted to use only local resources due to the limitation in terms of bandwidth and latency as soon as you leave your rack. However, if we are successful in building a network that can provide homogeneous bandwidth and latency across the entire data center, what this means is that we can provide the illusion of a single pool of resources. And in fact, since we have a very fine-grained time synchronization, we can also consider this as a synchronous system. So think, for example, what you can do if you have thousands of FPGAs all belonging to the same clock domain. Okay, and on this positive note, I'm going to conclude. So I hope I convinced you that by co-designing the stack and by taking advantage of the cloud scenario, it's possible to build a nanosecond optical network at data center scale. You can find more information about this project as well as other projects that are looking at optics technology in the context of storage and compute on our webpage. And I'm now more than happy to take all your questions.